Hi, everyone. My name is Karn, and today I'll be talking about our recent work called PIR-with-Default and Applications. And this is joint work with co-authors Tancred, Sarvar, and Mariana, and also our intern, Ni, who is now a postdoc at UC Berkeley. So first, let's talk about what the problem is that we're trying to solve and why we care about it. So the problem we're trying to solve is something called inner join, private join in compute. So what does this mean? So suppose we have a user who has a set of inputs consisting of pairs of IDs and integer weights, so xi and bi. And that we have a server who also has a set of IDs and associated weights, which is of substantially larger size. Then what we want to allow the user to compute is the inner join over the intersection. So that means for those IDs that are in both sets, the user should be able to learn the product of the user weight times the server weight, which we represent with v of x and w of x, respectively. And additionally, we may want the user to only learn this value with some noise added in order to achieve differential privacy. And the privacy property that we want to achieve is that neither party should learn anything extra beyond this output that the user receives. So just to say in a little more detail, the functionality we want to achieve is that the user should be able to learn the dot product of weights, perhaps with noise added, for the IDs that are in common between the user and the server. And in terms of efficiency, what we want is that the user's cost should be almost linear in the user's data size. And the assumption here is that the user's data is much smaller than the server's data. And this tilde, we use that to mean that actually the user's costs are allowed to grow in the server's data size, but they should grow very slowly as the server's data size increases. And to be more explicit about what we want in terms of privacy, we want that both parties' individual level inputs should remain hidden from each other. Furthermore, the elements that are in common should also remain hidden from each other, so no one should learn which items exactly were in common. The number of items in common should also remain hidden from each other, which is the size of the intersection. Note that these are all modulo that some of this information may be leaked just by the inner join of the intersection, but we shouldn't leak anything extra except for the inner join of the intersection. And the last one is we're actually okay to reveal the sizes of each party's inputs. So we don't consider that a privacy leakage. This is a privacy we want to achieve. And so the first question is, why do we care about this inner join, private join, and compute? Well, there's a couple of important applications. The first application is to achieve exposure notification protocol. So what's exposure notification? So suppose you have a user who has a set of Bluetooth keys which it's received from other devices that it was near at some point. And suppose each of these Bluetooth keys is associated with a proximity weight, which represents the signal strength or how close the other device was that was broadcasting that Bluetooth key. And suppose also you have a health authority acting as a server who has all the Bluetooth IDs for all sick users. So sick users would upload their Bluetooth IDs, and they also would upload virulence weight, which is kind of how infectious were they for, let's say, COVID-19 at the time when they were broadcasting this Bluetooth ID. So we want to be able to notify a user when they've been exposed to a lot of sick individuals or one very sick individual. And so one way we would be able to figure out whether or not to notify the user is perhaps by computing an inner join, private join, and compute. So that is, we might have the user compute what's the product of the proximity weight and the virulence weight for users this user was near and also turn out to be sick later. And we may want it to be computed privately so that we preserve both the user's privacy and the privacy of other sick users. And this value would be used to determine whether or not to show an alert to the user. Another application is measuring ad effectiveness. So here, suppose you have a merchant who's running an ad campaign and wants to see how effective that ad campaign is in getting users to buy stuff. So the merchant on its own would know which users visited their store and how much they spent, or at least for the transacting users. And an ad tech company who's running a campaign for this merchant would know which users have seen an ad. And perhaps it also knows a weight which represents how effective that ad is decayed to the transaction date. So in more detail, just suppose the merchant is only using as its input all the transactions that happen on a particular date. And the ad tech company has been showing ads for the 30 days before, let's say. Then this weight could represent how far in the past the ad was shown. Then one way to kind of measure the effectiveness of the ad campaign would be to compute what we're terming a weighted conversion credit. So this is like saying, oh, let's find out for the users who saw an ad how much they spent in total, but not just how much they spent in total. Let's find out the weighted spend value, and the weights we'll use are the time decayed ad effects. So in both these applications, the user or the merchant has a much smaller input set than the server. Like you expect a single user to be exposed to very few other devices compared to the total number of sick people in a country or under a particular health authority. And also for a merchant, you expect the number of transactions to be much smaller than the massive number of ads that may be shown for a particular campaign. Okay, so now that we've seen what the problem is and why we care about it, let's describe our broad approach and then more details. So our broad approach is to use a technique called secure multi-party computation. And secure multi-party computation basically allows two parties with private inputs to engage in a cryptographic protocol, which allows them to compute functions F and G over their input, while guaranteeing that nothing else is learned except these prescribed functions. And you can see that inner join private joiner compute is just a special case of secure multi-party computation, where F is the dot product over the intersection, and G is null or no output. So our approach is going to be to build a tailored MPC protocol for inner join private joiner compute and focusing on the asymmetric input size setting. So let's just see how previous work compares. So we have these properties that we want to achieve in terms of privacy and functionality and efficiency. So there's this actual previous work called Private Joiner Compute by Google, which allows computing on the intersection, but has poor efficiency properties for asymmetric sizes and also reveals the intersection size. There's also some unrelated external works which have either great privacy properties or great functionality or great efficiency, but not everything together. And so our work kind of achieves all the different criteria that we care about. And so now let's get into a very high-level overview of what our solution is actually like. Unfortunately, due to time, I won't be able to go into all the details, but I just want to give you a flavor of what we do. So the first thing we're going to do is build a primitive which we call PIR-with-Default. So PIR here stands for Private Information Retrieval. So our starting point is going to be from something called private information retrieval. And what is this? Private information retrieval is a special kind of MPC protocol which allows a user holding an index I to receive the ith item from a server who holds a database Y without revealing to the server which item they query. So it's a way to privately retrieve a database element. And crucially, the user costs here are almost linear in the user's input size, which here is 1. So it grows very slowly as the server's data size grows. So the first thing we're going to do is extend a standard private information retrieval protocol to enable, instead of querying on an input index, to instead query on an ID. So the user is going to be able to query on an ID X and retrieve the associated weight from the server if X is in the server's database, if the keyword or ID X is in the server's database. And in case it's not in the server's database, it'll receive some garbage output. So this is the first step to build a keyword peer. Then the next step is, instead of garbage, we're going to make it so that the user is going to receive a prescribed default value T. And this T is chosen by the server. Okay, so this is actually what we call PIR-with-Default. So it's a keyword peer where instead of receiving garbage when you're not in the server side, you receive a prescribed value. Then our next step is going to allow the client or the user to input its own value into the execution. And its output is now going to be its value times the server's value if you're in the set, otherwise the default value. And then our final step is to allow this to make it so the user will actually receive a masked output instead of the actual value. So that means the server is going to get to pick a random mask R. And now the user is either going to retrieve the product of the weights if the item X was in the server set, masked with the value R, or the default value chosen by the server, masked with the value R. And so we've kind of constructed this sequence of different peer with different cherries on top. And this thing is actually going to be really useful for us. And what we call is, this is extended peer with default. And so let's just step back for a second and see what is this thing that we built. It basically allows a user who has an ID and an associated weight to receive back something from the server, something that looks random to it. It's a randomly masked value. But if you remove the random mask from it, it's either the product of the weight, in the case that the item was in the set, or it's a default value if the item wasn't in the set. But the user doesn't know because it's masked with this random value. And so suppose we were able to build this extended PIR-with-Default. Unfortunately, I can't go into the building details because of time. But suppose we had this extended PIR-with-Default. We can now build inner join, private join, and compute from it in a straightforward way. So now let's go back to the case where we have a user and server with the inputs as we talked about before. The first step is the user is simply going to execute PIR-with-Default on each of its inputs, xi, vi. And the server is going to use the same default value, 0 each time, and a different random mask each time. Then what the user is going to do is it's going to sum together all the outputs it received from each execution to get a value T. So remember, each execution is either going to give it a masked product of weights or a masked default value, which is a masked 0 effectively. Then the server is going to sum together all the masks that it used in each of these PIR-with-Default executions. And it's going to send these mask values together with some noise. So this noise is going to be chosen so as to achieve differential privacy. And then the user is going to take the value T that it computed and remove this R prime value, which is a sum of masks plus noise. And this effectively unmasks the output. And so we'll get that for the items in the sum, for the items that were in common, you'll get the product of the weights. And for the items that weren't in common, you'll get the zeros, but you'll get them all added together and plus this noise. So this gives you exactly that the user learned the inner product over the items in common. And so this is basically our protocol. I didn't tell you how we did the PIR-with-Default, but you can see. And there's some important optimizations that are needed in order to make this efficient. And so we use some standard optimizations that have been used for PIR and PSI separately, but we put them together. So the first is slotting or batching, which allows PIR queries to be executed in parallel. And the second is to use a kind of cuckoo hashing technique that's from the PSI literature, which has the effect of greatly reducing the server computation. And so now I'd just like to show some costs from our experiments. So the first is to show that our costs, and especially our communication costs, grow very slowly as the server data set grows. So here, these 3 different graphs show for different client data set sizes, how does the communication cost grow as the server size grows from 100 million to a billion items. And our construction is the red line here, and you can see it grows very slowly compared to other solutions. And the y-axis is actually the logs in log scale. So actually it grows much, much slower than other solutions. And in terms of both communication and computation costs, our protocol compares especially favorably when the gap between the server and client data size is very large. Especially when, in the case when the server has on the order of hundreds of millions of items and the client has thousands of items. And also we measure in terms of monetary costs. So monetary cost is a good way to combine communication and computation costs. And you can see that while other solutions have approximately equal monetary costs for the client and server, our construction's monetary costs have far less cost for the client than for the server, and this gap increases as this discrepancy between the intersection sizes grows. So we get the desirable property that the party with the smaller input size bears fewer of the costs. And beyond the two applications we mentioned, there may be other applications, and we hope that you'll tell us if you have some ideas. And thank you, and feel free to reach out if you have any questions about them.